Yeah, hi everyone, welcome to my Maths Academy. In this video, we'll continue with Chapter 1 Relations and Functions from 12th Standard CBSE Mathematics. We'll continue from exercise 1.1. In the last video, we did till in exercise 1.1, problem number 1, second subdivision we completed. In this video, we'll continue from exercise 1.1 in page number 5 in your textbook. First problem, third subdivision, which is A is a set given as A is a set. A is 1, 2, 3, 4, 5 and 6, and the relation defined on A is R is a relation which is defined as set of all x comma y such that y is divisible by x. Y is divisible by x. Y is divisible by x. Y is divisible by x means y by x is an integer. Right? If we say suppose 24 by 4 means we can say 24 is divisible by 4. What is the meaning of this? 24 by 4 is 6. Then I say that 24 is divisible by 4. So y is divisible by x means y by x will be an integer, which means x will divide y. X will divide y exactly. That is the meaning of y is divisible by x. Right? Or you can also say y is a multiple of x. Y is divisible by x means what? Y is a multiple of x. Right? So many ways you can understand this, but this is how the relation is. Now we need to check whether this relation is reflexive, symmetric and transitive. Fine. Now how do we do this? Now solution. First we will check whether this is reflexive. Further, let's try to see if we can write the given relation in the roster form. This is in the set builder form where the definition of the relation is given. We'll try to write the relation in the roster form, which means we'll start listing the elements. So what is that? How do we write? So we have to take all the elements which will satisfy this condition. So the first element is what? 1 comma 1. Because the elements that we'll take from where? We'll take from A cross A. And A cross A is what? 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, then 2 comma 1, 2 comma 2. That is the Cartesian product of A cross A. From the Cartesian product of A cross A, we'll take one element and we'll check whether this condition is satisfied. If it is satisfied, we'll write that element in the relation. If it doesn't satisfy, we'll not write the element in the relation. Now we'll take 1 comma 1. First 1 comma 1. 1 comma 1. Is 1 is divisible by 1? Yes. So 1 comma 1 will come. Next 1 comma 2. Now 1 comma 2. 1 is divisible by 2. No, 1 is not divisible by 2. 2 is divisible by 1, but 1 is not divisible. So 1 comma 2, 1 comma 3. Is 1 is divisible by 3? No, 1 comma 3, 1 come. Then 1 comma 4. 1 is divisible by 4? No. 1 is divisible by 5? No. 1 is divisible by 6? No. So only 1 comma will come. Next is 2 comma 1. 2 comma 1 is 2 is divisible by 1? Yes. So 2 comma 1 will come. Then next is 2 comma 2. 2 comma 2, which means 2 is 2 divisible by 2? Yes. So 2 comma 2 will come. Right? So y is divisible by x. Right? Y is divisible by x. No, one second. I think we have to write it in the other way. Sorry. There's two other ways. So 1 is divisible by 1. Then now y is divisible by x. So we have to take, so 1 comma 1, 1 is divisible by 1. Next is 1 comma 2. 1 comma 2 means, okay, next element is 1 comma 2. 1 comma 2 means x is 1, y is 2. So which means we should say, if I take the next element, here it is 1 comma 1. So if I try to list down all the elements of A is 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5, 1 comma 6, then 2 comma 1, like that it will go till you have 6 comma 6. Now if I take 1 comma 1, right, then y is 1, x is 1. Is 1 is divisible by 1? Yes. Now if I take 1 comma 2, then 2 is y. Now is 2 is divisible by 1? We should read that way. 2 is y, x is 1. Is 2 is divisible by 1? Yes. 2 comma 1 will, sorry, 1 comma 2 will come. Because y is 2. So 2 is divisible by 1. Now 1 comma 3. If you take 1 comma 3, my x is 1, y is 3. Is 3 is divisible by 1? 3 is divisible by 1? Yes, true. So therefore 1 comma 3 will come. Similarly 1 comma 4 will come. 1 comma 5 will come. 1 comma 6 will come. Because y is 6. 6 is divisible by 1. 6 is divisible by 1. Right? Then let's take then 2 comma 1. 2 comma 1 if I write, then if I suppose 2 comma 1, we cannot write here because suppose if I write here 2 comma 1, we have to check is 2 comma 1 means y is 1. Is 1 divisible by 2? Y 1 is divisible by 2? No, 1 is not divisible by 2. 2 is divisible by 1. So 2 comma 1 won't come. 2 comma 2 will come because 2 is divisible by 2. Then will 2 comma 3 come? 2 comma 3 means 3 should be divisible by 2. Then 2 comma 3 will come. But 3 is not divisible by 2. Next is 2 comma 4. 2 comma 4 means 4 is divisible by 2. Yes, 4 is divisible by 2. So 2 comma 4 will come. Your y is 4, your x is 2. 4 is divisible by 2. Yes, then 2 comma 4 will come. Then 2 comma 5 won't come. 2 comma 6. 2 comma 6 will come because your y is 6, x is 2. Substitute here. 6 is divisible by 2. Yes. 6 is divisible by 2. So 2 comma 6 will come. Then next is we have to check 3 comma 1. 3 comma 1 won't come because 1 is not divisible by 3. So 3 comma 1 will not come. 3 comma 2 will come? No, because 2 is not divisible by 3. 3 comma 3 will come because 3 is divisible by 3. 3 comma 4 will come. 3 comma 4 should come means 4 is divisible. 4 should be divisible by 3. The second number should be divisible by the first number. Second number is y. First number is x. Second number should be divisible by x, which is y is divisible by x. Then that will come in the relation. Now 3 comma 4 won't come. 3 comma 5 will not come. 3 comma 6 will come. Yes, because 6 is divisible by 3. Now we should check next one is 4 comma 1. 4 comma 1 won't come. 4 comma 2 will come. 4 comma 2 should come means 2 is divisible by 4. 2 is divisible by 4? No. 4 is divisible by 2, but 2 is not divisible by 4. So again you are 4 comma 2 won't come. 4 comma 3 will not come. 4 comma 4 will come. 4 comma 5 will not come. 4 comma 6 will not come. Then 5 comma 1 will not come. 5 comma 2 won't come. 5 comma 3, 5 comma 4, 5 comma 5 will come. Then 6 comma 1, 6 comma 2, 6 comma 3, none of them will come. You will have only 6 comma 6 will come. 6 comma 6, which means second number should divide the first number. Second number should divide the first number. Fine. Now this is our set R. We have got the relation R. Now we need to check whether it is reflexive, symmetric, transitive and all that. Now to find reflexive, 1 comma 1 should be here, 2 comma 2 should be there, 3 comma 3 is also there, 4 comma 4 is also there, 5 comma 5 is also there, 6 comma 6 is also there. So we can say it is reflexive. That is one way. We have manually checked. We manually checked whether every element of A, 1 comma 1, 2 comma 2, 3 comma 3 means 3 comma 3. It is there or not, it is there. That is one way. Or we can also write general proof to show that it is symmetric, reflexive, to show that it is reflexive. So how do we write general proof? General proof is sometimes easy because here you have checked 1 comma 1 is there, 2 comma 2 is there, 3 comma 3 is there. That is one way. Or we can even write general proof. General proof, how do we write? We will take an element from A. We will say let A belongs to set A. I am taking one element from A. Then what I should prove? I should prove that A comma A belongs to R. Now when will A comma A will belong to R? When A is divisible by A. When will A comma A, both should be A. If both are A means here you put Y as A, X as A. Then read this. A is divisible by A. Which is true, right? Any number is divisible by itself. Right? So if I take an element from A, then A is divisible by A. For every A in A. Right? So therefore we can say A comma A belongs to R for every A belonging to A. Therefore, A comma A will be in R because A is divisible by A. If A is divisible by A, then A comma A will be in R because this statement is true, which means A comma A, here X is also A, Y is also A. So X comma Y, which means A comma A will belong to R for every A in A. Therefore, R is reflexive. Therefore, R is reflexive. Now we should check for symmetric, right? Now, how do we check whether it is symmetric or not? Now, let's take one element. So, 1 comma 2 is there. Is 2 comma 1 is there? No. 2 comma 1 is there, not there. So, we can say 1 comma 2 belongs to R, but 2 comma 1 does not belong to R. Therefore, R is not symmetric. R is not symmetric. Fine. Then the next one is transitivity. Now we should check transitivity. See, to check transitivity, we have to check whether this condition is satisfied. A belongs to B, then B belongs to C. Does it mean that C belongs to A comma B belongs to R, B comma C belongs to R? Does it mean that A comma C belongs to R? So we should take two elements of this pair. So 1 comma 1, and is there another element starting? Now once you take this element, take all the elements which are starting with 1. This is 1 starting with 1. Then check this. A comma B belongs to R and B comma C belongs to R. So A comma C, which is 1 comma 2, belongs to R. Similarly, if you try with this, it will belong. It will try with this. It will try with this. It will try with this. All are belonging, right? Now let's take suppose let's take 1 comma 2. Now 1 comma 2 and element starting with 2. This one 1 comma 2, 2 comma 2. So 1 comma 2 is there. Then 1 comma 2, 2 comma 4. So 1 comma 4 should be there. It is there, right? So any other thing starting with 2. This one 1 comma 2, 2 comma 6. So 1 comma 6 it is there. 1 comma 2. Anything starting with 2 other than this? No. From here starting with 3, it will satisfy. Starting with 4, it will satisfy. If you check for each two pairs, it will satisfy. So we can say it is transitive, or we have checked manually, or we can write the general proof like this. Either case we can prove, right? So we have checked for every pair it is satisfying. See, if I take 1 comma 4, anything starting with 4, this one 4 comma 4, A comma B, B comma C. Therefore A comma C, which is 1 comma 4, which is there. Similarly 1 comma 5, 5 comma 5, A comma B, B comma C. Therefore A comma C is 1 comma 5. Where this is A, this is C, this is B, this is B. So similarly 1 comma 6. So all will satisfy, right? So now we have checked manually and all are satisfying. Or we can write a general proof. How do we write the general proof? How we can write the general proof? If you have to show this, what we can say is general proof. How do we write it is? We'll take two elements. Let A comma B belongs to R and B comma C belongs to R. That is how we start. That is how we start for any transitivity proof. Will start A comma B belongs to R and B comma C belongs to R. Now we should prove A comma C belongs to R down the line. So A comma B belongs to R means what? B is divisible by A. That is the meaning of this. When A comma B belongs to R means B is divisible by A, and B comma C belongs to R means C is divisible by B. That is the meaning of B comma C belongs to R means C is divisible by B. Now B is divisible by A means what? B can be written as A. B is divisible by A means what? B can be written as some K into A. B is divisible by A means what? B is a multiple of A, which means B is equal to K into A. Something K into A. K is some integer. That's what we will say. If I say 24 is divisible by 4, if I say 24 is divisible by 4 means what? 24 can be written as 6 into 4. But 6 is an integer. So similarly, and C is divisible by B means what? So which means C can be written as some L times B. C can be written as some L times B. Now what we should prove? We should prove that C is divisible by A. What we have to prove? We have to prove C is divisible by. If C is divisible by A, then A comma C will be in R. Then our proof for transitivity will end. Now A comma B belongs to R, B comma C belongs to R means we should prove A comma C belongs to R. When will A comma C will belong to R? If C is divisible by A, then we can say A comma C will belong to R. Now we should prove that C is divisible by A. To prove C is divisible by A, we should prove that C is equal to something into A, some integer into A. Right? Now let's take C. So C is LB, B is LA. Now C is LB. The C equal to L into L is some integer. Where K and L are integers. Now L into B. B is what? B is Ka. So I'll put K into A. Now I'll get C equal to LK into A. L into K into A. So which means I can write my C as LK can be written as some M into A. So C is equal to M into A, which means what? C is divisible by A. C is divisible by A. That is the meaning of C is equal to MA. Any number, if you write that as something into A, then right, if you write 24 as suppose 6 into 4, then 24 is divisible by 4. Like C is equal to MA. So when C is equal to M into A means what? C is divisible by A because C is a multiple of A. C is a multiple of A means C is divisible by A. So therefore when C is divisible by A, then we can say A comma C belongs to R. C is divisible by A means A comma C will belong to R. Because we got this definition. C is divisible by A. If you apply here, C is divisible by A means Y is C, X is A. Which means A comma C will belong to R. Now we started with two elements A comma B belonging to R and B comma C belonging to R, and we have proved that A comma C is in R. Therefore R is transitive. Therefore R is transitive relation. Fine. So R is reflexive, but R is not symmetric, but R is transitive. Fine. Now let's go to the next one, which is the fourth one. All of you take the notes. Pause the video and take the notes. I will erase, and then we'll go to the next subdivision in the first problem. So we'll do in the first problem, fourth subdivision. So there what is given. Let's write what is given. See, always it is good to write what is given in the question and then what we have to prove. Once you understand what is given in the question and what we are supposed to prove, then proof is easy. Solving the problem is easy. Understanding the problem is difficult. Right? Understanding the problem is difficult. Once you understand the problem, then it is easy to solve it. So let's try to write what is given. So in the fourth one, given condition is Z, set of all integers. So Z, our set is Z. So dot 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 minus 3, minus 2, minus 1, 0, 1, 2, 3 dot 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 dot. That is our set of all integers Z. Now the relation defined on that is R, which is defined as set of all x comma y such that x minus y is an integer. X minus y is an integer. X minus y is an integer. Now we need to check whether it is reflexive, symmetric and transitive. Fine. So two numbers x and y are related. Obviously, see, x minus y is an integer. Obviously your x and y come from Z. X and y come from the set Z. Right? Now two elements are related when the difference is also an integer. Right? So see, here it is very obvious that because when two numbers are integer, when you subtract, then that will also be an integer, because subtraction, the operation subtraction is closed under, sorry, the integers are closed under subtraction. Integers are closed under the operation subtraction. That is the closure property of integers under subtraction, under the operation subtraction. Anyways, we will not get into that. You might have studied that in your smaller classes like 8th standard and all. Closure law, associative law, distributive law, commutative law and all that. So integers are closed under subtraction, which means when you subtract two integers, the result is also an integer. Anyway, so this R will become your Z cross Z. It will become a universal relation basically. Anyway, so we will prove that it is a, whether it is reflexive, symmetric and transitive. Now we need not list, we cannot write the solution. We cannot write R and then we cannot list on all the elements in R, because the elements will be like Z cross Z. The entire Z cross Z will come. Right? Because if I take 1, minus 1 is related to 0, because minus 1 minus 0 is minus 1, which is an integer. You take two numbers and if you subtract, if the result is an integer, then it will come, they are related. So here 2 and 3 are related, because 2 minus 3 is minus 1 is an integer. So every element is actually related to every other elements. Every element is related to every other element. Now we need to check all this symmetric, reflexive, symmetric and transitive. We should always do it in that order. First reflexive, then symmetric, then transitive. Now first one, we need to check reflexive. Now it is actually clearly reflexive, because 0, if you take 0 is related to 0, because 0 minus 0 is an integer. Now 1 is related to 1, 2 is related to 2, which means 2 comma 2 will be there, because 2 minus 2 is an integer, because 2 minus 2 is 0, 0 is an integer. Right? Now we are going to write the proof to say that it is reflexive, because you cannot find any number to disprove this. To say that, okay, I have a number 2 is there, but 2 comma 2 is not there in R. We cannot say that, because if I take 2, 2 comma 2 is there. If I take 3, 3 comma 3 is there. If I take 4, 4 comma 4 is there. But we can't say whatever I take it is there, therefore it is reflexive. We can't make a statement like that. We can't give a proof like that in mathematics, unfortunately. So which means we have to mathematically prove that 2 comma 2 is there, 3 comma 3 is in R, 4 comma 4 is in R, minus 2 comma minus 2 is in R, minus 1 comma minus 1 is in R. That we have to prove it. We have to write a proof. It's a very simple and easy proof. Right? So how do we do that? So we will say, first is to prove it is reflexive, we have to prove A comma A belongs to R. Now when can we say A comma A will belong to R? If A minus A is an integer. When can we say A comma A will belong to R? When A minus A, X comma Y will belong to R if X minus Y is an integer. A comma A will belong to R if A minus A is an integer. What is A minus A? 0. 0 is an integer, which we know 0 is an integer is true. So we'll start from that. We'll say 0 is an integer. We should start like that. What we have to prove? We have to prove that A minus A is an integer. We should prove that A minus A is an integer. Once you prove A minus A is an integer, then I can say A comma A belongs to R. For that, we are starting with 0 is an integer. That we know. But 0 can be written as A minus A is an integer. 0 can be written as A minus A, right? A minus A is 0. And this is true for every A. For every A, I take from Z. Every A I take from this Z. Every A I take, it is true. A minus A is 0. This is true for A minus A is 0 can be written as A minus A, and this is true for every integer that I take from Z. Now A minus A is an integer. We got this condition. A minus A is an integer. When A minus A is an integer, which means A comma A will belong to R. So which means A comma A will belong to R for every A belonging to Z. Now we have got this condition. Right? So therefore R is reflexive. So we have proved that R is reflexive. Now symmetric. Symmetric is also true because 1 is related to 2. Yes, because 1 minus 2 is minus 1 is an integer. Then 2 comma 1 is also related. The reverse is also related because 2 minus 1 is 1, which is also an integer. So if I try to take some example to disprove, and if you keep getting all the numbers are satisfying the condition, then it may be right. Then you should try to see whether I can prove it. We generally try to check whether for symmetric, we'll try to take one number from R and we'll say that number A comma B is there, and if B comma A is not there, then we can say it is not symmetric. But if I keep on taking one element from R, and if I am not able to show that the reverse is not there in R, means it is symmetric, which means we should prove that it is symmetric. So for symmetric, you can't take one example and say 1 comma 2 is in R. So and 2 comma 1 is also in R, therefore R is symmetric. We cannot say that. You cannot take one pair, one element and say, yeah, see, the condition is satisfied for this element, so it is true for everything. If you want to show that something is true, then you have to write a proof. But if you want to say that something is not true, which means false, then you can just, at that time, you can take one example and say that for this condition, for this number, say 1 comma 2 is there, but 2 comma 1 is not there, therefore it is not symmetric. We can argue like that when you are trying to prove that it is not symmetric. But we feel here it is symmetric because whatever example we take, whatever number we take, if I take 1 comma 2, it is in R because 1 minus 2 is minus 1, minus 1 is integer. The reverse is what? 2 comma 1. 2 comma 1, is it there here? Which means 2 minus 1 is an integer? Yes. Because 2 minus 1 is 1. It is an integer. Therefore, 1 comma 2 is there, 2 comma 1 is also there. Similarly, whatever I take, 3 comma 2 is there, 2 comma 3 is also there. 2 comma 4, 4 comma 2 is also there. So, for every pair or every ordered pair, the reverse is also there. So, which means we feel that it is symmetric. So, we can't say that now for every element I check, I feel that it is symmetric, the reverse is there, so I feel it is symmetric. So, feeling and all won't work in mathematics. We need to write proof. Right? We need to write proof. Right? So, how do we write the proof? The proof is simple. The only point that I am trying to make is, these are typical mistakes students do, saying that whatever they think, they will say because I think, so it is so and so. But we will have to write that what you are thinking is correct, but we need to write that as a proof, mathematical proof. Right now, symmetric will try to prove symmetric because I am not able to find any element where I can disprove that it is symmetric. So which means we should try to prove. Now how do we, so for the proof for the symmetric is we will take an element, let A comma B belongs to R. I should take A comma B belongs to R and I should prove B comma A belongs to R. The reverse should belong to R. So which means I am not taking any particular element, I am taking general element. If you want to prove something, you have to take general element. I can't say 1 comma 2 belongs to R and all that. That you can do 1 comma 2 belongs to R. To say that 2 comma 1 does not belong to R. And to prove that it is not symmetric, you can take one particular element. But for proof, you have to take a general element. So let A comma B belongs to R. Then when A comma B belongs to R, what does it mean? It means A minus B is an integer. This implies is an integer. When A minus B is an integer, then minus of A minus B is also an integer. Correct? If 5 is an integer, then minus 5 is also an integer. If minus 6 is an integer, then minus of minus 6, which is 6, that is also an integer. So when A minus B is an integer, then minus of that is also an integer. Why I am putting minus of that? Because if I put minus, it will become B minus A is an integer. This implies B minus A is an integer. Because minus of A minus B means what? Minus into minus plus B, then minus A. Now we have got what? B minus A is an integer we have got. When B minus A is an integer, then I can say B comma A belongs to R. So this implies B comma A belongs to R. So to get that B comma A belongs to R, to prove B comma A belongs to R, we should prove B minus A is an integer. And what we have? We have A minus B is an integer. How do I get B minus A is an integer from A minus B is an integer? This I have to get this. Which means I should put minus to this. Because if A minus B is an integer, minus of A minus B is also an integer. Fine. So when A comma B belongs to R, if we follow these steps, then we get finally B comma A belongs to R. Therefore, R is symmetric. Symmetric relation. I mean, if I say symmetric, it is symmetric. So only can put symmetric relation, reflexive relation. Just not writing that every time, but it is understood that it is reflexive relation or symmetric relation or transitive relation. Now next one is we have to see transitivity. So for transitivity also, if you feel it will look like transitive because if you take any element, 1 comma 2 is there, 2 comma 3 is there, both are in this because 1 comma 2 will be in R because 1 minus 2 is an integer, 2 comma 3 will be in R because 2 comma 3 is an integer. So 1 comma 3 also will be in R. A comma C will also be in R because 1 minus 3 is also an integer. So we cannot take any two elements like this to say that A comma C is not in R. We are not able to find such elements, which means it may be true. Right? We can get these two elements, but whenever I get these two pair of elements, I am getting A comma C belongs to R. which means it is transitive, so which means we should prove that it is transitive. So we have tried the proof. We can't say 1 comma 2 belongs to R and 2 comma 3 belongs to R, therefore 1 comma 3 belongs to R, therefore it is transitive. We cannot prove something is true by taking one particular element, or even two particular elements, or even three particular elements. You have to prove for the entire list of elements in R. And R is an infinite set. You can't, infinite number of elements you cannot list and prove. You have to write a general proof. So how do we start for the proof of transitivity? We will say let A comma B belongs to R and B comma C belongs to R. So that is the first step. If such a pair exists, then I should prove A comma C belongs to R. If such a pair does not exist, then also it is transitive. If such a pair exists and A comma C does not belong to R, then it is not transitive. Then it is not transitive. Now here we will try to prove that it is transitive. So the third part, transitivity part, is A comma B belongs to R and B comma C belongs to R. What we should prove finally? We should prove A comma C belongs to R. To prove A comma C belongs to R, I have to prove that A minus C is an integer. So finally what we should prove? We should prove A minus C is an integer. Now what is given? A comma B belongs to R. If A comma B belongs to R means A minus B is an integer. That is the definition of the relation. When A comma B belongs to R, here x comma y. Then x minus y is an integer. A comma B means A minus B is an integer. And B comma C belongs to R, which means and B minus C is an integer. That's what this is, implies. This implies A comma B belongs to R means this is true, and B comma C belongs to R means B minus C is an integer. Right? Now A minus B is an integer, B minus C is also an integer. Now we should prove A minus C is an integer. If I prove A minus C is an integer, then I can say A comma C will belong to R. Now our aim is to prove A minus C is an integer. Now how do we prove A minus C is an integer? Means we will start with A minus C. A minus C can be written as A minus B plus B minus C. Right? Because this is minus B plus B. They will get cancelled. You will get back A minus C. So I am basically subtracting B and adding B. I am subtracting B and adding B. So now that is equal to, why we are doing this? Because so now what is the value of A minus B? A minus B is an integer. So A minus B is an integer. So this is an integer. So this will be A minus B plus B minus C. But now A minus B is an integer, B minus C is an integer, and sum of two integers is also an integer. Sum of two integers, because integers are closed with respect to addition, which means integers closure law is true for integers under the operation addition. What is the meaning of closure law? When I add two integers, the result is also an integer. If the result is also an integer, then we say that integers are closed with respect to addition. Integers are closed with respect to addition, and that is called as closure law or closure property. Right now, so here A minus B is an integer, B minus C is also an integer, both are integers. Right? So we know that sum of two integers is an integer. Therefore, A minus C is an integer. Because this is an integer, this is A minus C. This is an integer, this is an integer. Why this is an integer? We have shown that A minus C is an integer. B minus C is also an integer. Then sum of two integers is an integer. So this is an integer. So A minus C is an integer. When A minus C is an integer, this condition is true. Therefore, A comma C will belong to R. Therefore, A comma C will belong to R. Now we start with A comma B belonging to R and B comma C belonging to R, and we got A comma C belonging to R. Therefore, R is transitive relation. R is a transitive relation. Fine. Okay. So we will stop here. I'll stop the video here. You can watch my next video for the continuation of this. You can pause the video and take these notes, and we will see you in the next video for the continuation of this. Thank you for watching this. See you in the next video, guys. Thank you.